let's start out with this. It's pretty obvious that the sun gives us heat and light. The question is, does it have a dark side? It's a great big light bulb, right? Well, we're going to build a solar radio telescope right here in Rochester, and you're going to see some details about why we're interested in its, quote, dark side. Let's try it out with this. Okay, so you may not realize it, that the sun is really our nearest star. Now, a lot of people don't think of it as a star because it's so close and so huge. But it really is a rather average, smallish, middle-aged star. The G2 just refers to its stellar color and what its makeup is. The fact is, our knowledge about it is only really very recent. 20 years ago, 50 years ago, our knowledge base of the actual sun itself was pretty minuscule. So, it gives us life, heat, and light. We need it for our crops, we need it for our survival. Well, what are the bad things? Are there bad things or dangers that we need to worry about? Sunburn, you're laying on the beach with too many Corona. That's one obvious one. But, what about some anomalies? What about some things like sunspots? I'm sure you've seen pictures of sunspots in the news. What about prominences and CMEs? Well, we're going to explore those things and why they can be trouble if we're not careful. So, first of all, sunspots, as we talk about, there's some pictures. Zooming in a little bit more and more on them. It's tough looking at this to get a sense of scale. How does the Earth compare to these guys? It's tough to, in your mind's eye, to put that relationship up there. Well, there's Jupiter. Now, Jupiter's about 11 times the size of Earth. Not many people live there, so it's still kind of hard to get a feeling for what's going on. So how about something like that? That's the Earth to scale against a sunspot. Or that. It's huge by comparison. Just for your reference, 330,000 Earths would fit in the volume of the sun. Okay, so you know that there are sunspot cycles. There's a quiet sun. There's an active sun. There's a curve showing sunspots. We're down here just coming up the curve. You can see the actual data against the solid line that says that's the model, prediction model, if you would. There's a quite active sun. You can see quite a few more sunspots than on those other two pictures.
When was that?
I don't know, but one of the things here is to show you that here's a quiet sun in 96. It's building. 2001 here, it's probably what that picture came from before. And then it's receding back to 2006 to show you what the scale is like. So the secret behind sunspots is really magnetics. Think about your work with transformers and chokes. The secret behind sunspots is magnetics. And that's where you'll see in just a minute why you get these incredible pictures of the sun's surface is from magnetic fields under the surface of the sun.
Why has this last cycle been a bust, pretty much? It just hasn't been...
It's been slower starting than normal. Maybe if we knew a little bit more about how it happens, which you'll see a few clues tonight, it's not exactly like it's a crystal clock. There's a lot of dynamics going on. So take a look at this picture. Notice the north pole of this magnet and the south pole. Sunspots always happen in pairs. North is leading. Here, south is leading below the equator. Well, take a look at this guy. Magnetic field lines are like that in the northern hemisphere, and like that in the southern hemisphere. Okay, now, the reason why you see sunspots is the magnetic fields that are below the surface that come out in these loops prevent the surface, the active surface where the hot gas is rising and giving off light. Those magnetic fields block the transport of that surface layer, so that's why it looks black to your eye. Now, it's not really, really black. It's black against the surface of the sun. If I were able to take one of those sunspots and put it in the night sky, it'd still be way brighter than the full moon. So it's the relative difference. Your eye picks it up in your brain of what it sees there. Now, remember this thing with the magnetic fields. There's a solar spectrograph in orbit. Notice these areas here with a hydrogen alpha filter. This is commonly used by guys with Earth-based solar telescopes. This is a multiband from a satellite. Notice the same things. Well, take a look at this one. This is magnetics. And you can see there's a really good correlation between where those active areas are and the magnetics, the magnetic disturbances, the fields on the surface. Okay? Now, here's a picture of how sunspots propagate on the sun. The sun rotates. The sun, at the equator, it rotates faster than at the poles. It's about 25 days at the equator, and it's about 36 days at the poles. So what happens is, you see a differential rotation that may be one of the dynamos that drive these strange-looking magnetic fields. And here we show a diagram, what they call a butterfly diagram. And what's going on is you see, because the equator is traveling faster than the poles, sunspots frequently get pulled down towards the equator. And you can see the group of sunspots here, and what happens. You can see from its shape, that's frequently called a butterfly diagram for obvious reasons. All right? So, rather than that being something interesting, the sun isn't just a huge light bulb in the sky. It's rather dynamic. So, we talked about magnetic cycles. As the sun's rotating, that magnetic cycle gets twisted up. The equator stretches it out, and it gets wound up really good to the point where after 11 years, the magnetic field becomes so complex, it literally snaps. It can't support that long chain of twisted up shapes. And actually a new structure happens after that occurs, but the field is reversed. So if I was looking actually at polarity, not just intensity, you'd see that the field was reversed from what we saw before. So what does that mean? That means a new 11-year cycle starts, but with the orientation swapped. North-south orientation swapped. So there's an example of sunspot activities. There's the North Pole, north part of the magnet in each one of these. You can see the 11-year cycle from peak to peak, but this guy is really the South Pole. So it goes from north to south. In other words, it's flipping over every time. So after 11 years, the north-south order of leading, trailing those sunspots that I showed you, they swap. The polarity changes. So really, if you look at polarity, the sunspot cycle, as you were taught in high school, being 11 years, it's really 22 years, if you take polarity into it. All right? Now, what do you think sunspots might have to do with the Ice Age? Well, it turns out that the lack of sunspots may have something to do with our global weather on a long time scale. Now, I'm not talking about global warming. I mean, the rock under your feet is pretty big, so it's going to take a lot to heat it and cool it. But if you notice right here, there was a period of almost 50 to 80 years where there were almost no sunspots. And guess what? That period right there is when the winter severity in London and Paris got much worse. You can see it got very cold. They had another one here in the 1550s. Now these are actual observations, visual observations of sunspots. This green plot here. These dots are actually using tree rings to decide whether it was a good year or not. And it's pretty much common knowledge that if it's a good growing year, the tree has a good ring on it. But if it's a cool, dry year, the tree doesn't grow much that year. So they can actually look at these huge sequoia trees that they cut down and go through the rings and trace it back to what the weather was like, centuries long. Now, another one. How about sunspots and cosmic rays? Well, it turns out the inverse of sunspots and cosmic rays. Here's sunspots, and you can see a pretty much inverse relationship to the cosmic ray count. I have no idea why. And I'm sure there are others that don't have a reason why yet. There's still an awful lot of mysteries about this great big ball. We just don't know. Our tools to study it, as sophisticated as they are kind of poor. So, what's a prominence? Well, let's try to describe what a prominence is. There's an example. There's another example. There's yet another. Again, one of these things that's hard to put in scale to the size of the Earth. That's a scale shot. So if you thought sunspots were something, take a look at this. Enormous by any comparison. Okay? So, the third thing on that list that I told you about was coronal mass ejections, CMEs. What are they? Well, you can take a look here, here, and there are areas on the sun that it's actually spitting out material. The sun is losing material to the tune of about 10 million tons a year. 10 million tons a year. That's a lot of material. And these things come spitting out here at a pretty good clip. 300 to 800 kilometers per second. Now, I don't know about you, but my brain isn't calibrated for kilometers per second. So, take just 500 kilometers a second, and that's just under 2 million miles per hour. Unbelievable speeds. And they take about 2 to 4 days to get here. Remember, we're 93 million miles away. And they're going like a freight train, but they still take 2 to 4 days to get here. It's said that in just one of these events, just one, there's enough energy that it could supply the Earth's global energy needs. Not just the United States, everybody, for 1,000 years. Now, I don't know about you, but those numbers to me are incredibly large.
Too bad they can't tap it.
No kidding. I mean, if they could, we'd never have an energy shortage.
They'd tax it to death.
Probably. Well, you know how that works. They tax everything that moves and subsidize everything that doesn't. So here's an interesting one right here. Here's 3.5 cycles of the last solar cycles, 21, 22, and 23. Notice that these CME and X-flare events occur either at the peak or at the trailing edge of the sunspots. There's only one that seemed to occur at the leading edge. And right now, I don't think that anybody knows why. What's going on here that drives this strange behavior? Don't know yet. So you pretty much know that's the magnetic field of the Earth, Van Allen belts, you guys know all about that. But this CME, or this solar wind that's blasting our planet, would completely sandblast off our atmosphere if it weren't for the magnetic field that protects us from that. Now, last month, you guys had a talk about the ISS. It's no more than about 100 or 2 mile altitude, right? So from the Earth, it's barely off this little dime here. Think about what happens with geosynchronous satellites that are at 22,000 feet. They're out here. You want to make a good secondary on a transformer? Hang something out there and see what happens. All right? Now, think of a fireworks pinwheel spitting out material, and then take a look at this model. There's Earth right there. So picture the sun, this is looking down on the north pole of the sun, spitting out material as it's spinning. It's like a garden hose stuck to a bicycle wheel. All right? So as these things come across us, we need to be concerned about, number one, if it's a very large event, and number two, if it's aimed right at us, we may have some trouble. Now, everybody in this room would get just a little nervous if one of these things happened out in the parking lot. I guarantee you. All right? So, kind of like nearby. There's a couple of radio telescopes, and there's a beauty right there. So, one of the things I want you to think about is solar-induced blackouts. Say, well, what is that? Well, back in 1859, there was a super flare, a flare that was bigger than normal, called the Carrington event. And think about what the technology was in 1859. Telegraph was the most modern thing you could have. And when this event happened, the records show that telegraph machines were dancing off the tables, even after you disconnected their battery. So think about the voltage you're inducing in that line that stretched out a couple hundred miles. There's a report that one of them, the coils got so hot it actually caught fire. Now, just imagine what that kind of thing would do to our Earth today. To show you, one of these events in 1989 actually took down the entire power grid in Quebec, Canada. Over 5 million people were out without power, some of them for more than a week. You know, you just don't go back and turn this back on like a light switch. You got to go out and disconnect your loads and then slowly bring them back online as you're generating more current. You can't just flip the whole thing on at once. So with that in mind, I want you to think about what would happen today with weather satellites. You know, weather satellites here, your DBS, DirecTV, and all that kind of stuff. And not to mention these guys down at the terrestrial level. Quite frankly, you can easily start making electronic popcorn. It wouldn't take much to knock these things offline if you're generating currents orders of magnitude greater than anything we've ever seen before. And that's a distinct possibility. You say, well, why hasn't it happened? Well, we've got a few examples here of where we happen to be in the right spot at the right time. So far, we've been kind of lucky. Number one, whichever major flares there have been, they've not been pointed right at us. Remember, it's a 360-degree ball, so it could be squirting out in any set of locations. You just got to be lined up on the right axes. So given that, and given what that amounts to, I want you to think about a project that we want to start here in Rochester. We've already begun the project here in Rochester. It's called the Solar Spectrograph, and what its intention is to study RF emissions associated with sunspot activity. All right? Its goal is to correlate RF spectral emissions with visible sunspot activity. Now, you may or may not know that a visible solar observatory has just been brought online by my astronomy group in Ionia, New York. And there's its GPS locations. And there's a picture of the campus, if you would. There's 7 observatories. So our goal is to construct a solar spectrograph to record RF emissions. We got 3 phases, 3 major phases. The first one is to have basic light, a receiver, computer to control it, and SkyPipe, which amounts to an electronic chart recorder, like the old paper chart recorders you guys might remember. The second one is to add tracking, right ascension and declination, and system control software, so it's not just a manual operation. And then the third is to enhance the sensitivity with a low noise amplifier, an LNA, and get ourselves internet access for file sharing to the global eCallisto site. One of the things you might say is, well, where the hell is Ionia, New York? Well, if you look at Rochester, it's down here in West Bloomfield, just over the border in Ontario. And there is the Google map look at it. And there's the dish that we're going to be using. There's its locations. So, there's the eCallisto network. Notice something. There are no receivers in Canada or the lower 48. They're grouped in Europe, some in Asia, one in Alaska, some down here below the border. So we, being in Rochester, would really fill a big blind spot between England and Alaska. They're very happy to have us do this project. And lastly, it would give us the ability to put our data on their global network for predictions and models and things like that. So, early attempts tried to use some surplus radar gear. They were pretty much in the 2 to 4 gigahertz band. They had down converters and all that kind of stuff that, you know, us old timers might be more comfortable with. So, what are we talking about? Well, the antennas that they use today are log periodic antennas. Most everyone in this room knows what I'm talking about when it comes to an antenna. And they kind of look like that, only on a much larger scale. The good things about these guys is they've got good gain and good beam width. The bad things about them is they got a back lobe that can sometimes cause you some trouble and grief. Now, our intention with this project is to use a dish. That dish, 7-foot dish, is about 180 times the surface area of what you saw in that previous 9x14 little wraparound. And we're going to take this active feed front end and make it the feed horn for this dish. So essentially we're going to replace this piece with this piece. So it'll give us great front to back ratio with the reflector, really good signal to noise ratio, so we can study the sun in relative peace. Now, why would we be possibly interested in some configuration like this that no one else is using? Well, it turns out that in Ionia, right there, these yellow dots, yellow and black dots, are where all the TV stations are. Notice they're all to our north and to our west. So what we're trying to do is turn our back to those megawatts and look south, which is where you see the sun most of the time. Okay, so there's a method in our madness.
Hey, Marty,
Yeah,
can I ask a question?
sure.
So when you have that log periodic facing the focal point of that dish, you still have a lobe coming off the back.
Yeah, but remember the back is now pointed towards the sun.
Right, so aren't you going to get out of phase signals because you've got some hitting into the back, some bouncing off the dish and hitting into the front?
Well,
You
the
get
guys
cancellation,
that
phase
modeled
cancellation.
that don't think that that's going to be significant compared to the
the
reflected
gain you're
signal.
going to get from
Yeah.
it. Okay.
So, oh, I'm sorry.
Are we gonna have to have a quiet zone for that?
Well, as it turns out, Ionia is a fairly decent quiet zone, and you're going to see why, with where we're physically positioned, the topography is also to our advantage.
Yeah.
All right? You'll see that in a second. So here's the dish. Here's the mount that it's on today. North is over here, so it's kind of like an equatorial mount. This is the declination axis. For you ex-Navy guys, declination is like elevation of a gun turret. All right? And right now, you can see that it's changed by a half-inch Craftsman socket set. This is bolt right here. The right ascension is the x-axis. That's the horizontal axis. And just to calibrate your brain, there's 360 degrees in a circle. The Earth goes through 1 day in 24 hours. So essentially, our spin rate is roughly 15 degrees per hour. So remember, if you're just standing there fixed, the Earth is going to change by 15 degrees in an hour. Okay? So, you got to aim this guy, and we're going to use linear actuators to do that. They come in 36 and 24-inch sizes, and this is just the insides of one. This is a geared down motor. This is a rack, a limit switch, and a little scale you can't quite see there that tells you how far out the linear actuator is extended. Now this one happens to have been out in the weather a while, so I don't know that we're going to use it depending on what we find when we fire it up. But, oh, I'm sorry.
Would have thought you need a bigger dish for this, wouldn't you?
Well, the sun's pretty bright, and if you get the right setup, you don't.
Oh, that's true.
It's not like we're trying to find Pluto, right? So the receiver part of it, the eCallisto receiver, is a frequency agile receiver. There's a picture of it. It covers 45 to 870 megahertz spectrum, and it can take 300 kilohertz slices out of that tuner. So think of it taking real fine slices of cake. That's what you're doing. Take 800 samples a second. It's software controlled. And there's an example of one of their prototypes run by a laptop. Ours is probably going to be a desktop because we need more storage space and speed. So picture in your mind's eye, you have this spectral envelope here, and you grab the remote and start banging on the up channel button on the remote. All right? So away you go. Oh crap, I got the wife's remote by mistake. So you're banging on the up channel of the remote, and it's going along. And you happen to see a TV station that's an offending emitter to you. So you have the ability to drop that guy out of the data before it pollutes your entire data set. Now, I don't know that anybody's considered doing this before. Think of it like a digital filter. You guys know how LC filters work with marginal Q. Well, this is a digital filter. So we could select throwing that channel away without affecting the two on either sides. Rather an interesting way to approach things. There's an idea of what the receiver's like. No good hardware engineer can just resist not taking the covers off of it. There's the tuner right there. There's the microprocessor that controls everything. There's the antenna input. Notice here, serial port to the computer. You can even put in a high accuracy crystal clock for it to run off of, like a slave, if you're trying to run two of them, for example. And there's what the system in Alaska looks like. I happen to have the fortune of meeting Whitman Reeves, who's a RF engineer, consultant in Alaska, does a lot of work for like maritime radios, that sort of thing. And he has a hobby of doing this. He was in one of my radio astronomy classes in Socorro, New Mexico. So here's his setup right now. You'll notice the LNA, or low noise amplifier, his log periodic antenna, the antenna rotator, just like you would use for your TV antenna rotator, and software that controls that rotator. All right? Now, when you collect all this data, imagine 800 samples a second over that frequency band. Most all of you are used to looking at a 2D plot of something, like in this case frequency or time against whatever you want on the vertical axis. In this case it's noise figure. Could be amplitude, could be a bunch of stuff. That's like a 2D slice out of one channel in that data set. What do you do when you're sucking them up at such a rate that you get buried by the data? Right, there's your frequency. Well, here's a typical plot from their output. Now, those of you that are old Navy guys that might be submariners, you might recognize this as a waterfall plot from a submarine sonar.
Or PSK,
Yeah,
the thing called PSK.
yeah. So frequencies on this axis, 45 to 826. Time is on the horizontal axis. So that whole plot there is less than 15 minutes worth of data.
Wow.
Take a look at some things. So it's taking slices as you're going through there constantly. Notice this red guy might be this guy right here. You say, hey, what is that? Well, it appears to be about 245 megahertz, and it occurred exactly at 2 hours and 3 minutes, all the way down to a 10 microsecond clock. It's a timestamp. You say, well, gee, that's rather interesting. Also, look at here. It's not constant. I bet you this was a data channel up to a satellite. You know, even your local auto parts store has a satellite link that they can order parts, et cetera, et cetera. And I don't know if you can see it, but there's a few underneath this line as well. These guys are probably TV stations that are near him. All right? So, in phase 2, one of the things that we're trying to decide is what is the best way to digest all this tsunami of data. You might think of a plot like this that you might see in like Excel, or one like this, but this would only be ganging together a few slices to see what's going on. I like these kind of plots. You can get a lot on a like a topographical map, like a wireframe model. You can get a lot of information in one of these. But I think one of the best ones I've seen is something like that. So you can catch a small peak hiding behind another peak. You get that 3D look at what's going on.
What is red versus the green signal?
Those are just different frequencies. In this, it's a simulated plot. It's not actual data on this one. Okay?
That's impressive.
So, here's the low noise amplifier, and I think you guys will appreciate this. Coming right in the front end, a great big honking lightning arrestor with a number 10 or number 8 wire to a nice big solid bolt.
That could be enough.
All right. Here is the actual amplifier itself. Here's a band reject filter, power supply to run the amplifier. And this bias tee is something you're familiar with, is how do you couple DC into a coax in order to power the stuff up on the pole. All right? And here's a typical one in a system setup. The way he's got it engineered, he can actually run 2 of them off the same antenna box. And then this is just the power supply and the 2 receivers. I don't really believe he's doing this, but it has the provision that if you wanted to add 2, you could have 2 essentially piggybacked on the same system. So, what's our goal here? Well, if you saw the newsletter article, you saw that I mentioned educational outreach. What does that mean? Well, it's to mentor young engineering students. Now, think about this. You guys are wizards. You just don't know it. And I'm sure your wife probably hasn't called you that. But just think about the years of experience in this room right now. The centuries of experience. Young engineers only know about this. They're cramming theory between their ears. They know nothing about practical design techniques. So, I don't care if it's electrical engineering, computer engineering, software, or mechanical, every design methodology includes key design steps. First of all, you got to get the idea in your head. You got to lay down some system requirements, have an engineering concept. At this point, it's a cartoon. Right? After that, you start forming a schematic, be it SPICE for electronics, AutoCAD if you're mechanical, or I don't know if John's in the house, or CAD if you're an optical engineer. You start to take this and you start to simulate it or fine-tune it. What is the tolerances I need on these components? You do that with these 2 guys, or if it's AutoCAD, things like linkages. Then you end up with a board layout or a physical layout of a chassis and the actual prototype. This is the first time, as you well know, you've got a piece of hardware to hold in your hands. Now, I'm not trying to put anyone down, but these guys here don't know what they don't know yet. And if you remember some of your first projects, there's a lot of scar tissue that go with fixing all those warts that showed up in the prototype.
Second-degree burns.
Yeah, exactly. So here's the thing. After this, you got to do this, and that's where all those warts get fixed, hopefully. And then you verify that it does what you say it was going to do. Well, you're still not finished. If you happen to be in industry, you had to worry about production build. Now you built one of them. We want to build 100 or 1,000 or 10,000. Try that, you know how tricky that can be. The story doesn't stop there. Take a look. You need to worry about field service. You need to worry about all those things that go with these things. Really, really good design houses put their junior engineers in at this phase of the program. You'd be amazed the look on a junior engineer's face when he goes in to adjust the pot and the hole in the panel is a ½ an inch off from where the pot is. He says to himself, holy shit, I'm going to make sure when it's my turn I fix that. Or when he goes to replace the circuit board that he doesn't have to disembowel the entire machine in order to get a thing out. Those are practical things you guys do without even thinking about it. But for engineers, young engineers that have never experienced it before, it's a trauma. They don't know what they don't know yet. What's that famous NASA quote? There were unknown unknowns, right?
Runs with the access panel against the wall.
So now think about this. Even this is not the ultimate. For the key to really good designs is to looking at failure modes. What's a failure mode? If a part's going to fail, what's the most likely way it's going to fail? All right? Now I know you let the smoke out, right? But if you're in life support or flight safety, it even shows up in car and truck design these days. Life support, how would you like to be the guy that got the one bad pacemaker out of 50,000? I don't think I'd want it to be me. Just ask Boeing about flight safety. When you have a battery service call, you can't roll to the side of the road and call AAA, can you? Now, this shows up in even your car. How many people here drive a car with an automatic transmission? Almost everybody. Well, modern automatic transmissions are controlled by computers. And if there's something that screws up in that transmission and it can't control what gears you're in, let's say the solenoid box, you've got a lazy solenoid, doesn't want to switch, it actually defaults to second gear. It's a limp home mode or limp in mode that doesn't leave you stranded on the side of the road. I mean, the really great designs incorporate these kind of things. So where does that leave us? Well, it's a design outreach. You might ask yourself, why the hell did you pick astronomy? And my contention is, it's the only field of science that covers so many different engineering disciplines. So optical engineers for mirrors and lenses, they frequently design lenses to an accuracy of a hundredth wave or better. Mechanical engineers need to design a very stiff structure. If the structure's like rubber, it doesn't do those lenses much good. All right? You got mechatronics where you actually bury electronics into this design to give you active surface control. And I'm sure you've seen articles where they actually bend mirrors while they're looking at the wavefront to give you very little aberration, optical aberration. Well, guess what? They do that in radio astronomy as well. That's the Green Bank telescope that's looking down from on top. It's 1.5 times as tall as the Statue of Liberty. It's 578 feet tall. You're looking down from on top, and those are 3 guys working on the panels. Look like ants crawling around on a dinner plate. But each of those panels, at the corner of those panels, is a servo motor that goes up and down. And a laser just over my shoulder beams down at a little retroreflector and decides what the height is like and moves that panel up and down to the accuracy of a human hair. Now, that dish is the size of Bill's Stadium. And if it's sitting like this or sitting like this, gravity is pulling on that and is going to distort that shape. Those servos make it into an ideal shape, irregardless of which way it's pointing. Now, something that big, if you're a electronics power engineer, that telescope weighs just shy of 17 million pounds. Now, I'm sure you've seen the traction motors on these huge diesel locomotives that they're making. There are 16 of those in the base just to turn it, just to rotate it. All right? Now, on the other end of the scale, you know low noise RF design. If you want to make a low noise amplifier, you're dealing with pretty minuscule things on that end of the scale. That's the opposite end of the scale. That's microwatts and nanowatts as opposed to megawatts. All right?
How do you keep all those servos from getting in your signal?
They've got them well shielded. Matter of fact, it's shielded better than you would the shielding that they use on aircrafts. It's double shielded and everything else. We're going to add servo control to our telescope, as you well know. In computer engineering, they get involved in all these kind of things. Control software, LabVIEW, I'm sure some of you have seen LabVIEW, you use it like the front, operator front panel. Radio Sky, now this is an interesting one. How many of you have seen a picture like Starry Night, a planetarium program, or went to the planetarium, where they could synthesize what the night sky looks like, the visual night sky looks like? This guy is the radio equivalent. Where are the radio sources in the celestial spectrum, as opposed to the visual ones? They are not all the same. Some things put out in the visible, some only put out in the radio. Okay? And certainly RFI, if you got to figure out what you're going to do if somebody nearby is banging on your door that prevents you from doing your job. Data collection and reduction, like we were just talking about those plots before. Image processing, I'm sure you've seen stacking programs that take visual pictures and stack them up and then vote on where the pixels should really be. I mean, there are an incredible number of disciplines represented here, all under that one title. Right down to the point where, besides the data servers that you're going to send this data off to, even a civil engineer, think about it. If the building that you're in is too hot during the day, it's going to be cooling off at night. Just like when you're driving down the road in the summertime and you see the heat rising off the pavement, that's what that building is doing. So the telescope is trying to look through that at a star. Stars don't twinkle, by the way. It's the atmospheric perturbations in the air we breathe that causes it to look like that. So you need a building that's going to stay rather cool in the daytime. That's why most observatories are either silver or white. And it's going to try to stay cool, stay at constant temperature at night, so it doesn't perturb what you're trying to look at. Now, you look at the number of disciplines contained there that are engineering related, and I challenge you to come up with another field that's so diverse. It's going to be pretty hard to do. So, what does that mean for us? Well, here's a timeline for the solar spectrograph. We've got to do a site survey looking at east-west. In other words, just how much of the sky can we see at different times of the year. And that's one of the things that I'm involved in right now. I've got a program for my iPad that lets me impress GPS coordinates on a physical photograph. So I can take a photograph of the sunrise at noon and sunset and tell with a pretty decent precision what my angular span is going to be for that servo, for that physical location. And that's something I'm just involved in now. Hopefully if the weather was a little bit better, I could get that done in the next couple of weeks.
That's a cool app.
Yeah, I thought it was rather interesting. And you could either have it as GPS or magnetic, the heading, which I thought was rather interesting. One of the first things we got to do is configure the control computer that you saw in those previous pictures. Integrate eCallisto receiver number 1 with the PC. We ordered 2 receivers, a primary and a backup. Our primary receiver is coming fully assembled, fully characterized, for the following reason. We need to tie this to the PC to start our software development cycle. A lot of software to integrate here, so we need an engine to do that on. All right, the site survey that we talked about, this is the physical geometric site survey. This is the RF equivalent. I've already gone to the site and taken a simple DTV, flat screen TV, powered it up with that active antenna I showed you before, and ran through the channels at the top of the hill looking north, at the top of the hill looking south, and then coming down the hill. We're on the south face of a hill, so the transmitters, the TV transmitters will be at our back. So we're down the hill a little bit, and I repeated that test down there. And it was just my crude way of saying, how bad are these megawatts going to kill me from all these TV stations? The next step is actually to take this receiver, tie it into a dipole, and see generally where are my interfering frequencies, and then take a directional one and figure out radially whereabouts are they compared to where we're going to position that dish. And then there's a program called Frequency Genie that helps you isolate those offending emitters.
Boy, you're gonna have a great time when the museum fires up their kilowatt spark trap.
Thanks. You could have not told me that.
We'll invite you down, we're only about 8 miles east.
Oh, no.
Always gonna do it in the Rochester
So-
area with no sun.
Well, that's why it's a radio telescope.
You do that at night though, right?
For your reference, Rochester is one of the top 10 cloudiest cities. It comes in at number 6. So that alone is a good reason to use a radio telescope and not an optical one. And if you're feeling bad that we're number 6, think about Buffalo. They're number 3.
That's why Kodak
So-
says the world's largest darkroom.
Yeah, and you didn't even go inside. So the second receiver is really coming as a partially assembled kit. The board is assembled. It's on the matter of fact, it's going on the burn-in rack next week. All of this stuff is burned in for a minimum of 72 hours. But when it gets here, it's going to be with the pieces for the connectors, that shell, that case that you saw. And that's an opportunity for some of you guys to teach engineers how do you assemble something like this. Remember, a lot of these guys haven't even had the experience to know how to solder.
Oh, boy.
Yeah, I'm just telling it like it is. I'm not trying to make it up. They're used to book learning. They're used to getting crammed with theory. They don't always have labs that lets them do active projects like this.
Give him a Bergmatic torch.
There you go. One of the things, that antenna that I showed you, that little Turk active antenna, that's meant for indoor use. So we got to design a weatherproof enclosure that allows it to use it outside at that feed horn and then mount it to the dish. System software, one person mentioned it earlier. That's a list of just the basic system software that I got to start loading on that PC before I can do day one of anything. Steering servos, linear actuators for right ascension and declination. We want to do sun tracking. Well, there's what a linear servo looks like. Here's the motor, gearbox reduction, the 2 limit switches, and a little encoder to tell you how many turns. Now the geometry here is about 1 foot. This axis along here is about 2 feet. So think about it. From middle to the end is about a 45-degree angle. Gives us 90 degrees. That's about 6 hours worth of sun, with the sun looking. You're essentially de-rotating for the Earth. The Earth is rotating, and you're pointing it the other way to keep it trained on the same thing. So that's about 6 hours worth of movement. This one uses a 3-foot one, which has, instead of 45 degrees, it's about 56 degrees. That gives you about 7 hours, 7.5 hours. You say, wait a minute, the day is a lot longer than 7 hours. Yeah, well, if we were in Nebraska in a cornfield that I could see the horizon at sunup and the horizon at sundown, sure, we'd have a whole different problem. But remember, from that picture I showed you before, we're sitting in a cleared out spot in woods, so I'm sure we're not going to get 12 hours of tracking. Just ain't going to happen.
You can't see the horizon in Nebraska, all you can see is corn.
Yeah, well, there you go. So, I mean, unless I go out there with a chainsaw, which people are not going to be too happy with me, our neighbors are not going to be too happy with me, I'm not going to see probably a lot more than 7 hours worth of sun tracking. And then, this one's rather interesting. All the designs today use a horizontal log periodic antenna. No one has looked at using vertical polarization at this guy. So what we're talking about doing, this antenna, as you can see here, you can either mount it this way or this way. There's a regular conventional coaxial fitting that you and I are used to, but it's set in a square piece of plastic. So I thought one of the really interesting design things would be, design me a little servo in a circular fashion that can rotate the antenna from horizontal to vertical, so that while we're sitting up looking at something, we can take a scan both ways. No one has looked at vertical polarization
How about
in that
circular?
whole network. Well, circular, you'd obviously have to have a different feed. You'd have to have a helical
Yeah, but
feed.
that was
again-
another thought, is circular polarization is,
No doubt about it. I'm saying we're trying to push back this unknown list little by little. Sometimes you got to do it by, baby steps.
one at a time is good.
So,
What you need is an EMI antenna that comes with the switch.
yeah. So, I mean, really, that's the long and the short of it. What I'm really looking for as part of the membership here is to say, hey, who do you think might be interested in participating in some of this stuff? The 3 colleges that I'm talking to are Roberts Wesleyan, where I teach, U of R, that has a pretty decent engineering and astronomy section, and especially RIT with their RF labs. So you'd get a first-hand chance to work with these guys, teaching them about the real world. I mean, you know, I say it with tongue in cheek, but there's centuries worth of experience in this room. You're embedded in it, so you might not see it that way. And for your interest, if you'd like, sign on to the ASRAS website, Rochester Astronomy. If you plug just ASRAS and Rochester Astronomy into Google, that website will come up. And there's my email, both at school and at home. And I've got a sign-up list that you can leave me your name and number and tell me if you think you're interested in something like this, and maybe what are some of your background experiences that you'd be willing to share with young students. Now, when you get a chance to look at that ASRAS website, excuse me, when you sign on to the website, in the lower center of the screen, you're going to see a screen that looks like a radio telescope. And if this ever comes back to me here, come on. Come on. It's thinking about it. I guess. Just give me a second here. Wonder why I can't see the rest of the screen here. Sorry guys, what I wanted to do is show you what the screen looked like. I'm having trouble closing this file. I can't seem to see that. Ah, there we go. There we go. So when you sign on to the ASRAS website, you'll see a radio telescope in the middle center of the page. And when you do that, when you bug that link, it'll take you to about 5 or 6 pages that explain about radio astronomy. Why do radio astronomy? You know, the why, the brief history, light is light, a pixel, and the projects that we're involved in. There's 3 main projects that we're involved in. And the first one is a DBS satellite, little 12 gigahertz DBS satellite. And it's a project to allow scouts and high school students actually track geosynchronous TV satellites. So they get a feeling for what radio astronomy is on a very basic level. This is a rather simple project. That actually is a scout group that built one. I have parts, so for someone that might be interested in doing this that maybe isn't so comfortable with meeting with professors or other students, this is a project. If you're handy, I'll supply you the parts if you're willing to build one. Ideally, I'd like to have 2, one at the site that people can use when they come down to the site, and one that would be out on the road on loan to science, science fairs, high schools, science labs, Boy Scouts, etc. The second project is what you saw here, what we're talking about today. And then this baby down here is where I want to go next. Now make no doubt about it, if you thought the solar thing was something, this is a capital project. We're talking anywhere from a 22 to 24 foot dish. You got one of those in your backyard? I'll be over with the truck tomorrow. So we're looking at 1.42 gigahertz, which is the protected astronomy frequency. And we're talking about trying to look at deep sky sites. Not just the sun, we're trying to look at things like Jupiter, radio noise on Jupiter, bright objects, bright celestial objects that emit in the RF. And there's one more project that I have down here that I've not yet announced because I don't have enough data on it, or money. By the way, I got a grant for this solar radio telescope to pay for the hardware. And with the idea that, we'd be helping some young engineers carry on this profession. I mean, think about RF engineering. To a lot of people, it's become a black art. So what better way to teach young engineers that might not have a sensitivity for it, to sit them in the lab and have them build some of this stuff? Then it's not so intimidating. Okay? If you got any questions, please, don't hesitate. That's it.
Just a comment too. I'm from the Rochester Academy of Science Astronomy section. I'm on their board, and wanted to be here to. And Marty's a member there. To invite you to the site, to try to get down involved in some of these projects that we do. We've got a total of 10 buildings altogether.
Yeah.
But we've just built last year we put up a solar telescope system, so if you can actually see a visible solar telescope system, so you can see prominence coming off the surface, at those fine frequencies. So try to encourage you. We're looking at this whole area of astronomy and radio. I mean, there's a tight fit. As things happen in the night sky, or the sky is what ionizes, how you're operating with HF and everything else you're doing. So we're looking at this at the cusp to say, we could really work together on some of these things. The astronomy section has funded so far and has been giving Marty money to get some of this stuff off the ground and get it built. We've approved that, and we've approved a lot of other construction items. There's an 18-acre site down in Ionia. So I want to encourage you. So how do you get involved? Our meetings are right now, the same time.
Yeah.
Friday night, first Friday of the month, we have our general meeting during the winter over at RIT. In the summertime, we meet down in Ionia at the facility. I think some people, Kevin, I think you live down that way, right? In fact, Kevin, you think you're with the fire department down there, right? So he's right across the street from it. He can give you directions. But there's a lot of people that, as you have in your group, that can't come to the general meetings, but that will show up and do events. With the solar equipment, you've got daytime events. With some of the astronomy equipment, you've got nighttime events. So what is it to be a member of the Academy of Science? The Academy of Science for an individual is $10 for the Academy. And it's $17 for the astronomy section. And that's an annual thing, so it's very, very, very cheap. If you want to be involved in other groups, the rock and mineral and birding, you can again join those too. But I just wanted to give you that encouragement. As a family, instead of $17, it's $22 for everybody in your family. We have annual events. On the site, there's Rochester Starfest, and we bring in speakers. We have usually a couple hundred people. We have dinner provided outside. There's camping is always free in the site. A lot of great things. People during the winter do cross-country skiing there, and we try to take good, citizen care of this. So, any questions with the Academy of Science? I'm just trying to open the can. So I'd encourage you to be involved and be members of that group too, and I think it would be a great fit.
Yes.
What's your estimated date to get this done by?
I'm sorry?
Your estimated date to get this done by?
Well, I'd like to get the basic step 1 done by the summertime. So at least the first light, if you would, by this summer. That's why we structured the way we bought some of the parts, to get us to where we could start loading some, software and things like that. Now, the engineering projects, obviously, that's going to be dependent on how many people we've got, how many, students we've got, to see how fast we can go ahead on that sort of thing, on that partnership side of the scale. I personally think it's a win-win situation. For some of you, you say, hey, I'm not ready for the rocking chair yet. I'd like to find myself doing something once I retire. Well, then you got young engineers that don't know what they don't know yet. So it'd be your way to teach them, and then besides all of that, we end up with building a system like this. Now, I'm not operating under any delusions. I don't expect to see our name on the list for the Nobel Prize in Astronomy, but even if it's a technological flop, which I'm certain it won't be, even if it is, look at what you've done. You've educated people that can't get this kind of knowledge in a classroom. They just can't. And that point was driven home to me last year. I was teaching an electric circuits course, and there wasn't a lab. And I went to my department head and I said, how in the hell can you think you're going to teach a circuits class without a lab? So I went off and made a lab. You want to see the look on these kids' faces the first time I set them down to a simple DC series circuit. I just taped over the value of the resistors and said, here's the circuit you want to put together. You're going to measure voltage and current and figure out what that resistor is. Well, God, the first day it was like a deer in the headlights. They didn't know what to do. But you know, after the first 2 weeks, I had kids coming in saying, hey, what are we going to do this time? And I don't know about what your learning curve is, but when I was a kid, when I was a teenager, I worked on my own car, so I was used to turning a wrench. And I'm sure a lot of you guys did the same thing. Oh, you're doing that now once you're retired. Working on your receivers and everything. There's nothing like putting hardware in your hands to help you learn. And I think that's really what we're faced with here. Unless you want nothing but theoretical physicists out there, which I don't think helps our economy and our profession, our work profession very much. It's a way to teach these guys that the real thing is hardware in your hand, because that's what you do those designs for. You don't do them for some concept on a piece of paper. So personally, I think it's a win-win situation. Yes, Gary?
Can I ask you two related questions?
Sure.
The data that you guys are going to be pulling down, is that going to be remotely accessible?
Yes. Actually, what we're going to be doing is we're going to be uploading our data to a central file server that all the network of receivers are going to dump their data on. And yes, it will be remotely accessible.
And then the second question, who can access it? Can regular people or just members of the club or who?
No, the eCallisto system is on the air. It's right now, it's not mostly, I shouldn't say that. It's amateurs, it's educators. There's a cross-section of the population that accesses it.
So I can pull some data down and play
I
with it
think
at
so.
home? Okay.
Any other questions for these two gentlemen?
Let me mention one other thing, just as an encouragement. We believe in what Marty's going from the Academy of Science. We funded that initially. We've been talking to people from the Farish and Woke Foundations and so on, looking forward to try to build some more. What they've asked us is how many people are interested. And if we come back to them and say, you know, we really don't have, we have a low interest in this, nobody's interested in radio, nobody's interested, then this just kind of slowly slides away. But if this picks up, we're actually getting funding for this. And they've taken us at our word going forward. We've put initial funding to get this started. And we're looking, we're actively looking. That's why Marty's pushing us along. So I'm trying to encourage you, you know, as both an educational for the Rochester area, for assistance, what can you do to help? And if it shows that, oh my goodness, we had 50 people show up to start piling this in, doesn't mean you're always there, then they can, you know, we can go back to these groups and says, we have a large group in the community that's actively interested in this. And I guarantee we'll get more funding. But we're fighting for funding just like everything else. You know, there's a lot of programs out there. But we think radio is important. We think astronomy is important. And we just thought it's a great fit between the two groups. We've got the property to do it, so, okay, thanks.
Yeah, we've got funding and a site, which are two of the
I want to
biggest
encourage you.
problems right off the bat.
Marty, I want to thank you. Excellent
You're more than welcome.
presentation this year. And thank you for coming this evening. Safe journey home. See you on the 23rd.